welcome back. This is another video where we look at some of the fundamentals of electrophysiology. In this video, I would like to introduce you to the language of electrical engineering. One really amazing tool that electrical engineering gives us neuroscientists is a language of abstraction. To simplify a lot of the complexity of ion channels, all that stuff, we can simplify it and operate at a higher symbolic level to actually understand how electric signals are generated in neurons. And in this video, I'll show you the basic components, the individual elements, and in the next one, there will be another one where we talk about the rules, if you will, the syntax, how we put these elements together. So the first component I would like you to learn about is the resistor. The resistor is a device you can buy to put in your electric circuit, and it has a specific symbol which looks like this. I usually call it R. The property of the resistor is called resistance. Now, you can also have resistance wherever you have 2 points, and you can understand how hard or easy it is for current to flow through. So we can also use resistance not only to describe a resistor we can buy for our electric circuits if we're interested. We can also use the same concept, for example, to explain how hard or easy it is for ions to cross the cell membrane by passing through ion channels. So the question we always want to ask about these individual components, and in general when we think about electric signaling, whether it's an electric circuit or a neuron that we want to model, is how does current and voltage relate to each other? So current flows along this conductor here. Let's call this IR, the current through the resistor. And there's nothing magical happening, so the same current, of course, comes out down here. So when we think about current, we go somewhere in the diagram, like where I drew these little arrows, and we say, what's the current there? You can think of it almost like a cross-section and see how much charge carriers pass through per unit of time. Now, voltage is different. Voltage is between 2 points and relates to the amount of electric energy it takes to get from one to the other point. So voltage, we usually draw as an arrow next to a component between the 2 points. And essentially, the voltage is the difference in electric potential between these 2 points. So this is how it would look like. Let's say V or VR for the voltage across the resistor. So how does voltage and current relate to each other? It's a very straightforward linear equation that is called Ohm's law. V equals I R. R in this case is a constant. So when we think about a plot where we relate voltage and current, in this case, if voltage is on the y-axis and current is in the x-axis, there's a line here with slope R, and the line goes through 0. Now, later on, it will be useful to think about this in a slightly different way. So we can also say I is our dependent variable. I equals V divided by R. And those are the kind of plots where V is on the x-axis and I is on the y-axis that we typically use in electrophysiology. It's again a straight line that goes through 0, but now the slope is 1 over R. Now there's actually a term for that. So it's called conductance, or G. And it makes sense that it's an inverse relationship, so the larger the electric resistance is, so 1 divided by this, the smaller the conductance is. Now just very briefly, the physical units for resistance is ohm, like Ohm's law, and we usually use a capital omega. And for conductance, we're using a S for Siemens. So this is the electric resistor or resistance. We know in a very straightforward way how voltage and current relates to each other, and the physical units of resistance are ohms. In neurophysiology, we often use conductance, which is 1 over resistance, and the physical units is Siemens. I'll see you in the next video to talk about some of these other circuit elements we'll need to model the electric behavior of neurons. Take care.